Well, hey, it's Dr. J. Today we're going to learn about absolute extrema, also known as extreme values. And there are different types of extreme values. We have already talked about local maxes and mins. And I haven't really explained why we use the term local. In fact, up until now, I could have just simply been calling something a max or a min. So today we're going to define what we mean by local. And then we're going to broaden our definition to a bigger world, which we call global max or min. And so all of these things are what we call extreme values. So first we'll talk about local. So let's start with a maximum. So X, a local max, also known as a relative max, maximum of f of c occurs at x equals c if f prime of c is equal to 0 and f double prime of c is less than 0. So we call this a local or a relative maximum. So this is the point C on the x-axis, and then on the y-axis, remember y equals f of x. This is the point f of c, or the value f of c. It's the y value at c. So we call this a local max or a relative max. All right, so why do we use the word local? Well, we use the word local or relative because this y value f of c may not be the largest y value in the whole world. And I'm going to use the whole world in quotes. Yeah, that's why we use the word global in the whole world. And really the whole world is, in other words, the domain. The domain of a function is what we consider the whole world, right? The domain of x, or the domain of f, which is the x values here. So we don't know. We only know locally. And so this is what we call a neighborhood. Yeah. So this is called a neighborhood. Neighborhood of x equals c. So when you are near this point, now there is a proper definition. I'm using the intuitive definition of a neighborhood, but a neighborhood intuitively means near to the left and to the right. And we call this a neighborhood. We've used that term before when we were talking about limits back, several months or a couple months ago, however long it's been. So in this neighborhood, this is the largest y value, but we don't know what happens outside the neighborhood. You know, the function could go way up here and be higher, you know, when it gets outside the neighborhood. Or maybe over here. Yeah. So there could be larger numbers, larger y values outside of this neighborhood. So what we say is, well, locally, as long as the first derivative is equal to 0 and the second derivative is less than 0, then we say it's a local maximum or a relative maximum. All right. Similarly, we define a local or relative minimum of f of c at x equals c if, well, f prime still has to be 0, but the second derivative would then be greater than 0. And all you have to do is turn this picture upside down. Okay. And as long as we are near C, we have some sort of neighborhood. Neighborhood is very loosely defined in this lecture. In a more advanced calculus course, we might specifically define what's called an epsilon neighborhood, where you'd have, you know, this point plus epsilon to the right and then minus epsilon to the left, and it would get very technical and detailed. But for this course, at this level of introductory calculus, we're just going to say close to, similar to how we did it when we were talking about limits. And again, the first derivative is 0. So that means there's a horizontal tangent here. And the second derivative is greater than 0, which means it's concave up. And so this is a local minimum. All right. So again, it might not be the lowest point in the whole world or in the entire domain. As you get farther away, who knows? You know, there might be a point out here that's lower than that point. So we don't know, right? So we can only say that it's locally the lowest point on the graph. Okay. So we've already been finding these points in the first derivative and the second derivative lectures. We've been finding these points for, you know, a couple weeks now, but I didn't really define them specifically because it didn't really matter at that point until today, when we have a second definition of absolute extrema. So absolute now. So f of c is called an absolute, or a global maximum occurring at x equals c if f of c is greater than or equal to f of x for all x in the domain of f. Okay, in the domain of f. And I will put a note, there are two types of domains. Domain can be implied. This is what we call the natural domain. Call that an implied domain. Or it can be defined explicitly. This is what's called a restricted domain. So there are two ways to define the domain. It can be natural, which means that I give you a function and I don't say what the domain is. I probably won't do that in today's lecture, but maybe I'll do it. I'll do it once just to kind of tell you how that works. But the most common one, at least in this part of the course, is I specifically or explicitly define what the domain is, and we call that a restricted domain. You saw that in the last lecture with the application problems, where we said it has to be greater than 0, but less than, whatever, 5 or 12 or whatever. We put a boundary or a limit on how big the values can get. That's what we call a restricted domain. All right, so this is an absolute extrema. Right. It means that it is, in fact, the largest value in the world, global, and the world meaning the domain. Okay, and then of course, now I always recommend, writing these down, having them in your notes. But if this were, a memory recall test where I wanted you to memorize these, I would say I would tell you to memorize maximum, and then you get minimum for free just by turning around this inequality. So watch how easy it is to get the second definition. To change it to minimum, you only have to do one thing, and that's change the inequality to less than or equal to. And then we have a global or absolute minimum. Okay. So the classic example of a global minimum or maximum would be a function like this. So suppose I have x squared minus 2x minus 3 okay. The domain is not explicit. Right. So the implied domain is negative infinity to infinity. In other words, all real numbers. Right. There is no restriction on this function. It's just implied that the domain is all real numbers. I'm not going to use the grid on this one. I'm just going to draw a rough graph. All right. F prime of x is 2x minus 2. Set this equal to 0. I'm skipping the steps here because this is something we've done a million times. I'm going to add 2 to the other side. I'm going to divide both sides by 2. And at this point in the course, you should be able to do that pretty quickly. You get x equals 1. So at x equals 1, that's my c. Right? From the definition. Now remember, this is not the minimum or the maximum. This is where it occurs. Right? F double prime of x is just 2. So f double prime of x is positive. So that means it's a min. Yeah, concave up. So let's plug in f of 1 and find out what that is. Go up to the original function and plug in 1. And you're going to get 1 minus 2 minus 3, which is negative 4. Oh, man. Did I just break my phone? Nope, I didn't break it. Sounded like it broke. 1 squared is 1. 2 times 1 is 2. Minus 3, so that's negative 4. So this point here is negative 4. All right. So it looks like this. If I wanted to plot another point, I could plot a point. It crosses the y-axis at 3. Negative 3, sorry. Okay. And that's not a very good graph, but it's good enough, right? It's good enough for this example. So this is the lowest point in the entire world, but it's also satisfies the definition of being a local extreme or a local minimum. So this point, negative 4, is a local minimum and an absolute minimum, or a global minimum. I use those words interchangeable. It's both. It is both locally the lowest point on the graph and globally, because in this domain, negative infinity to infinity, no point is going to be lower than this point. Right? Because this parabola just keeps going up and up and up and up and up. And so this is the way we say it. We say a local min and global min of negative 4 occurs at x equals 1. Sometimes we omit the word occurs and we just say at. If you just say at, it's implied that I mean occurring at, but sometimes I say it. So we say the y value first. The global min of negative 4 occurs at x equals 1. Sometimes we switch it. We'll say at x equals 1, a global min is negative 4. Sometimes we say it that way too. The key is the word at. At tells you where it's occurring at, and that's always the x value. The word of is sometimes replaced with the word is. The global min is negative 4. Of and is are interchangeable. All right, now that's an implied domain. All right. I should also mention that there is no local max, dne, and there's no global max, that's dne, on this domain, because the domain is negative infinity to infinity. Now, if I restrict the domain, I have to tell you that at the beginning of the problem. So watch this. Watch how we can do this. I don't even have to make a new function. In fact, it's easier if I don't for this introduction here. Let's use the same function. I will call it example 2, though. Oh, my pen is running out. I might be switching colors today. Switch to the blue team when my black runs out. Okay, so if I want to restrict the domain, I usually put a comma, or sometimes we'll put the word when, or sometimes we'll put the word for. This is what's called a restriction. And I will tell you what type of restriction I want. This is called a restricted domain. And we usually use square brackets for less than or equal to or greater than or equal to. So we have x is greater than or equal to -1 and less than or equal to 4. So the restricted domain as an interval or interval notation is square bracket -1 comma 4 with another square bracket. So that's definitely not an implied domain. If I want to restrict a domain, I have to explicitly tell you that the domain has been restricted. And what that means is that it does not go on to infinity. Right? It stops at, say, at 4. And over here at -1. It's as if the world ends at -1 and at 4. There are no x values outside of these numbers. The whole world exists in this strip between -1 and 4. So let's now do example 2 with the restricted domain. We have to plug in the endpoints. So this is what we call the left end. F of -1. So that'll be -1 squared minus 2 times -1 minus 3, which is 1 plus 2 minus 3, which is 0. So that dot's right there at 0. And then at +4, the right end, f of 4. These are points, so sometimes we say left end point, right end point. F of 4, we have 4 squared minus 2 times 4 minus 3, which is 16 minus 8 minus 3, which is 5. So 1, 2, 3, 4, 5. Again, I'm not using the grid, so it's not to scale. And there you go. So this would be a restricted domain function, or the same function with a restricted domain. And so now the results are slightly different. We have a local and global min of -4 at x equals 1. So that result stays the same. We have only a global max of 5 at x equals 4. So this point here is a global max. And this point right here is both a local and global min. All right. And then this point is neither. Yeah. It's neither local nor global nor max nor min. It's none of the above. It's just an endpoint. I should mention one more thing before I erase this example. A local minimum could possibly be both local and global. That is possible. Right? However, a endpoint cannot be local, can only be global, or nothing at all. Yeah. Never local, because the derivative does not exist at an endpoint. Since f prime of x does not exist at an endpoint. Either one, left or right, it cannot be local max, yeah, or local min. It can't be local anything. You cannot apply the word local. Right? So in order to apply the word local, the derivative must exist. In fact, both derivatives have to exist, the first and the second. And remember, an endpoint cannot have a derivative because it's discontinuous at that point. All right, going all the way back to the definition of the limit on the left and the limit on the right, well, have to agree with each other. Well, this does have a left-hand limit, but it doesn't have a right-hand limit because there's no graph on the right-hand side of that point because it's been restricted. So that's how different the answer can be by restricting the function. Okay. Let's try another example. All right, well, example 3. I turned off the camera very quickly and drew this so you guys didn't have to sit there and watch me create a graph, which can be very time consuming. So we have a cubic polynomial function on a restricted domain from -9 to 3. So I've drawn that out for you with the endpoints. The y scale is very large. We're going by 200s here. And we can kind of already see what's going on just by looking at it, looking at the graph. Here, it's a non-extreme value. It's just an endpoint. It's not a max, not a min. Here we have a global max. Now, it looks like it's close to 800. But I don't want to trust it. I can estimate it about 800, but I should probably plug it in to see. And so that's where the x value comes into play. The x value, let's look at that very carefully. So we've got right about here, this is our max. We'll call it the G max. And it looks like x equals -7. Yeah. Notice because the derivative is equal to 0 here, right, it's also a local max. So it's a global and local max. This board takes up all my space. All right, so I can tell that just by looking at the graph. And then here at x equals 3, we have a global minimum of, I don't know, at x equals 3. Now, because it's an endpoint, it's not local. So we do not say it's local or relative. We say it's only global. So this one's a global max because it's not an endpoint. Yeah. So now we want to find the y values. So we'll use the original function here. So we'll plug in -7. Do some scratch work down here. So what do we got? -7 cubed. Oh, I got a cube button on your phone calculators. That's -343. Oh, times 2. So -686. We got -7 squared, which is 49 times 12. So we got 588. Put that where you can see it. We got -126 times -7. That's positive 882, and then plus 3. So that's going to be our maximum value. So let's see, 882 plus 3 is 885, plus 588 is 1473, and then minus 686. 787. That is our global max. Which kind of makes sense looking at the scale here. Oh, it's global and local. Our global minimum at 3. So do some scratch work for f of 3. So we got 3 cubed. Most of these we can do in our head. 3 cubed is 27 times 2. It's 54. 3 squared is 9. 9 times 12. I feel silly doing that on the calculator. That's 108. Plus 108. 3 times 126. That's negative, so it'll be -378, and then plus 3. So I got -378 plus 3, plus 108, plus 54, gives me -213, which looks about right based on the scale. So notice, because I already had the graph, I didn't really need to take the derivative. If I didn't have the graph, before I do the next example, without the graph, I could verify f prime of x is 6x squared plus 24x minus 126. I think those are all divisible by 6. So I'll set that equal to 0. Divide everybody by 6. Now, I'm not sure if 126 is divisible by 6, but we'll see. Yep, it is. So that'll become x squared plus 4x minus 21. Then I would factor this. X plus 7, x minus 3. And so I get x equals negative 7. Check. That's this point here. And then x equals 3. That's this point here. Now, because it's an endpoint, it doesn't get the title local minimum. However, if it was not an endpoint, so if the restricted interval went past 3, I mean, even if it only went to like 3.1 or 3.5, or just all it has to go is any decimal, infinitesimal, fractional amount past 3, right? Then 3 would be part of the differentiable domain, right? Or the domain of the derivative. So we know that f prime of negative 7 is 0, check, but f prime of 3 is dne because 3 is an endpoint. So I know I'm really belaboring that point, but it is important. It's an important distinction between, being able to take the derivative at a point if it's in the middle of the interval versus not being able to if it's at the end of the interval. Okay. I didn't bother with the second derivative, but I mean, I could. Let's just do it really quickly before I erase. The second derivative would be 12x plus 24. If you plugged in negative 7, you would get negative 84 plus 24, which is negative. Yeah. And so that's what makes it a maximum. Remember, if the second derivative is negative, then it's a maximum. We already knew that because we had the graph, but we're not always going to have the graph. In fact, I think I'm only going to show you one more graph today, and the rest of them we're going to do what we call blind, which is, I mean, you're not really blind. You can see the graph without actually drawing it. You can see it in your mind by using the derivatives. That's kind of what a derivative does. It gives you a mathematical, image in your mind without actually turning on the lights, without actually seeing the function. So here's another cubic. And we're on a restricted interval. I have room to write the interval negative 5 to 9, positive 9. Okay. So there's our restricted interval. So again, off camera, I went ahead and drew the graph of this one. So here's the graph. Goes from negative 5 to 9. Again, I have a magnified Y scale here. Got a little smudgy here when it was off camera. So again, we have a endpoint at negative 5. So let's just do a summary. So we'll go from left to right, at x equals negative 5. There is a non-extreme value. Of, I don't know. I'll have to figure that out later. At x equals negative 3, That's a local min. And again, I don't know exactly what it is. I know it's negative, somewhere between negative 200 and 0. If I really had a good scale graph, I could zoom in on it and get it down to a particular unit, but I can't do that. So this is a local min. It's clearly not a global min because there's a point that's lower than that. Right here at 4, we have a local max and global max. Yeah, it's both. It's both locally the largest y value in that neighborhood, and it's also the largest y value on the entire graph. That looks like 4, for being very careful with the grid there. X equals 4. We have a local and global maximum. Again, I don't know what that is yet. I'd have to calculate it. And then finally at x equals 9, that's just global minimum of, I don't know. So I'm going to answer all of these I don't knows by using the function that's given. Well, let me go ahead and label this. This is a G min, global min. Oh, and then keep in mind, local is sometimes called relative, yeah, and global is called absolute. So we use different terminologies depending on the question. Okay. All right, let's do a little scratch work. Get your calculators ready, and none of these are like powers of 10. 10s are usually easy. 1s are easy to calculate, and 0s are easy to calculate. Unfortunately, none of these are those types of numbers, so these are all going to be very time-consuming. But we can do some of the work in advance. It saves you a little bit of time. Negative 5 cubed is negative 125. So you can just kind of do that part in your head and then multiply by negative 2. You could probably have done all that in your head. So that's f of negative 5. Scratch work over here. So that's 250. Now, most of this I think we can do in our head. So 5 squared is 25 times 3 is 75. 72 times 5. Can you do that in your head? Probably by the time I type it out, you'll go, oh yeah, 360. 72 times 5. And then plus 95. So that's negative 360. Because it was negative 5 times 72, plus 95, plus 75, plus 250. So a non-extreme value of 60. And if you look at the graph, at this endpoint, that looks about right, yeah. It's positive. It's very close to the x-axis because the scale is a magnified scale. Being very close to the x-axis, it's less than 100, so 60 makes some sense. Let's do negative 3. So negative 3 cubed is 27, negative 27. Negative times negative times negative, and then times negative 2. So that'll be positive 54. I think we do the next one with our minds. Negative 3 squared is 9. 9 times 3 is 27. That one was pretty easy. Negative 3 times 72 is negative 216. If you're not sure about that, do it. 72 times 3, 216. And it's negative because multiplying positive times negative. And then plus 95. So negative 216 plus 95 plus 27 plus 54, negative 40. Again, that's this point here. L min, local min, negative 3. Yeah, it seems right. It's negative. It's below the axis. And it's between negative 100 and 0. So negative 40 seems reasonable. So if you get an answer that's just way far away from what it looks like, then you probably need to double check your calculation. All right, 4 cubed is 64. 4 times 4 times 4. And then times negative 2. Negative 128. 4 squared is 16. 16 times 3 is 48. I'll do it just to be safe, but I already know it's 16 times 3. It's 48. That's positive. The rest of these are all positive. 72 times 4, 288. 288. And then plus 95. Add those all up. And then the first one's negative. Negative 128. 303. I'm going to double check that. So I got 48 plus 288 plus 95 and then minus 128. Double check. Yeah, 303. I can also double check it on here. That's my local max. All right, that's 200, that's 400. It's kind of in the middle. Yeah, it looks pretty close to the middle between 200 and 400, so 300 seems reasonable. All right, and then finally our global minimum, which is way down here. So we're estimating it's somewhere between negative 400 and negative 600. All right, so what do we got? 9 cubed. 729. And then times negative 2. That's 1,458. 9 squared, that's 81. 81 times 3 is 81 times 3. 243. 9 times 72 is 648. And then plus 95. So 648 plus 95 plus 243 minus 1458, negative 472, which again makes sense if you look at the graph, right? It's somewhere between negative 400 and negative 600. It's almost to negative 500. So for the rest of the questions, I don't want to be bound by the graph. I would like to be able to just say that it's a maximum or say that it's a minimum. You can always return to the graph if you need to visualize the result. So maybe I'll do quick sketches if it becomes something that I want to illustrate. But I want to first talk about a theorem. It's called the extreme value theorem. is a very useful theorem. It basically guarantees that we will have both extremes, a maximum and a minimum on a closed interval. So if a function f is continuous, right, so it can't have any asymptotes or holes. Again, you remember the definition of continuous from chapter 1. On the closed interval AB, then f has an absolute maximum and an absolute minimum at A or B or some point C between A and B there's an easy way to say this using alligators. So some point C between A and B where f prime of C is equal to 0. So it guarantees that you're going to have an absolute maximum and an absolute minimum either at the endpoints, yeah, A or B, or at some point in between. All right. Now this or is not necessarily exclusive. So you could have both. You could have a maximum at one endpoint and then a minimum in the middle somewhere, right? The diagram is actually quite simple. Kind of just imagine this type of a picture, yeah? So you have A, B, yeah, and then some point C. There could be more than one. So if there's more than one, we'll call them C1 and C2. So there could be more than one, possibly more than one. So in this diagram, there's two C's. Here's what it would look like if there was only one C. Yeah, so you have an A, a B, and then a C. So this is the extreme value theorem. It basically guarantees that we will have one of each, one maximum and one minimum on the interval. All right, so let's go ahead and see an example of this theorem. Example 5. F of x equals 4x squared minus 4x plus 10 on the interval 0, 8. So this is A, this is B. We're going to find C. So we're going to take the first derivative. Yeah, first derivative of 4x squared minus 4x plus 10 is 8x minus 4. We're going to set that derivative equal to 0. And the solution is whatever you get here. Yeah, that's our x equals c. All right, so we're going to solve this. Add 4 to both sides. Divide by 8. And you get 1/2. So that's our c. Okay. C is 1/2. Notice it's on the interval. It's between 0 and 8. So now, without actually drawing the graph, we're guaranteed that we're going to get one maximum and one minimum. Absolutes. It's the absolute extremes. All right. So I need to go back to the original function. So f of 0 is 4 times 0 squared minus 4 times 0 plus 10. So that equals 10. F of 1/2 is 4 times 1/2 squared. You can use 0.5 if you prefer. So what's that? 1 minus 2 plus 10. So that's 9. And then f of 8 is 4 times 8 squared minus 4 times 8 plus 10, which is 4 times 64 minus 32 plus 10. 276. Let me just double check that. 64 times 4, 256. I'm glad I double checked. Minus 32 plus 10. Plus 10. 234. So the largest number is the absolute max. And the smallest number is the absolute min. And that's what the theorem says, right? So this is A. This is f of A. This is f of B. And this is f of C. And the theorem says you're going to get an absolute max and an absolute min either at one of the endpoints or at some point in the middle. And so we got one endpoint and one point in the middle. All right. And then I want to make sure that you say it correctly. So the way you say it is you say absolute max is... or you could say of 234 at x equals 8. Or you could say global as well. Absolute min is 9 at x equals 1/2. And occasionally we reverse it. We'll say at x equals 1/2, the absolute min is 9. Yeah. So the order doesn't matter, but the key is the word at. Yeah, the at tells you where it's happening at. And then sometimes instead of is, we'll say of. And then instead of absolute, sometimes we'll say global. So, math is just like any other language. We say the same thing in lots of different ways. Gives us a rich, diverse language. It also makes for more opportunity for customization and individual thought. So your mind, I hope, will hone in on one version of how it's said, and that'll be the one that you like the most. So 4 minus 3x squared on the interval -4 to 1. Again, there's A, there's B, and then we're going to find C. And there could be more than one C, but and so far there's only been one. So the derivative of 4 is 0. The derivative of -3x squared is -6x. You don't really need to say 0. You could ignore that. All right, so then you set this equal to 0 and solve. To find C. So whatever your solution to this is, that's your C. Divide by -6. Remember, C means critical value. 0 divided by -6 is 0. So our critical value is 0. So now we test it using the original function. I usually do them in order. So I do A first, then I do C, because C's in the middle, and then I do B. Although the order that you test it doesn't really matter. Testing is also the same as evaluating. We're plugging in the number. Now, in some of the previous tests, we didn't really care about the answer. We just cared about whether it was positive or negative. In this section, because we're talking about maximums and minimums, we do care about whether it's positive or negative, of course, but we also care about the value, what you actually get. So that's going to be 4 minus 48, right? That's going to be 16 times -3. Be careful. That looks like 2 negatives, but it's actually 3 negatives because it's a negative times a negative times another negative. So it's going to be -44. So far, that's our min. Yeah, so far. Let's see. F of 0, that's going to be a very easy one to plug in. Just get 4. Yeah, because 3 times 0 squared is 0. And then 1 is also a very easy number to plug in. You get 1. 4 minus 3 times 1 squared, which is just 1. So this is our min. And then the larger one of these is the max. Absolute. Now, this theorem only cares about absolute maxes and mins. It doesn't tell you about the local. If you want to know which one's the local, you would have to either draw the graph or you could use the second derivative. And we've already gone over that. So in this particular theorem, I'm just asking for the absolutes. And the theorem is true every single time. So you're going to get one of each. Which one? 4 at x equals 0. I got them backwards, don't I? This one's minimum. This one's maximum. All right, got them right. Minimum, negative. See how the sign kind of pops out if you get them backwards. So minimum is -44. Maximum is 4. And then this is just a non-extreme value. Okay. How about example 7? Q minus 6x squared minus 63x on the interval -9 to 13. All right. So we got our A, we got our B. One strategy is to just plug those in now, and then you'll already know the two endpoints. I don't find that very useful because sometimes the endpoints don't end up mattering all that much, but you're always going to plug them in at some point. So it's either do it now or do it later. I like to focus on the calculus first, which is the derivative. Plugging in a number is not really even calculus. It's algebra. So there's our derivative. I'm going to set that equal to 0 and solve. Again, you can solve this by lots of different methods: factoring, completing the square, quadratic formula, lots of different ways. I always try to simplify before I solve. They're not always easy to simplify, but this one is. They're all divisible by 3. And then you could factor this out: x minus 7, x plus 3. I feel like we've seen this one before. Maybe I'll watch the video after the. I'm having like deja vu. We already do this one? If not, we did one very similar to it. All right. Well, I know we've seen the 7 and the 3 before. This is actually negative 7, so that means that the C value is positive 7, and then this is x plus 3, so the C value is negative 3. So we have two C's. You don't really need the subscripts. You could just call them C's like that, but you might get confused as to which one we're talking about. So there could be more than one critical value. All right. The C's are always between the two. We're only interested in the C's that are between the interval here. Okay. So if one of these C's is outside of this interval, then you could ignore it right now. So the C does have to be between. Now notice that both of them are between negative 9 and 13. So you should check that. 7, yeah, that's less than 13 and greater than negative 9. Yep, check. And negative 3, yeah, that's bigger than negative 9. Yeah. If you have to, you could draw a number line, but you'd feel silly if you did, but I'll do it. Here's 13. Here's negative 9. And then I've got my C1 is 7. And I've got my C2 is negative 3. And everybody is in the interval. So this is where we're looking. All right, let's go ahead and test them. You could do them in any order you like. Evaluating the function to find to test, if you like, who is the max and who is the min. I'm going to go from left to right. So we'll start with negative 9. I use the original function. So negative 9 cubed. Negative 729. Negative 9 squared is 81. 81 times negative 6 is negative 486. And then 63, negative 63 times negative 9 is positive 567. So just add these all up. And negative 729, and you get negative 648. So far, that's the minimum, but it's the first one I've done. I usually go in order, so let's do C2 next. Negative 3 cubed, that's negative 27. Negative 3 squared, that's 9. 9 times negative 6 is negative 54. Negative 3 times negative 63, that's a positive 189. And then add these all up. 54. And then minus 27. I always say add it up even when you're subtracting. Because subtracting is the same as adding. It's just adding the other direction, adding the opposite. Let's go to 7. F of 7, 7 cubed. Anybody ever memorize 7 cubed? 7 times 7 times 7. I feel like it happens enough that probably it's worth memorizing. 343. 7 squared is 49. 49 times 6 is 294. Negative. Negative 63 times 7 is negative 441. So I got negative 441 minus 294 plus 343. Negative 392. So far, that's the min. Negative 648 is still the min. And then F of 13. 13 cubed. I always forget I have the cubed button over here on my fancy phone calculator. 2197. 13 squared, 169 times 6, negative 6. So it's negative 1014. And then 13 times 63. 13 times 63. 819. All right, so I got negative 819. And then negative 1014. And then positive 2197. 364. Oh. All right. So look what happened. The points in the middle are non-extreme values. At least they're not absolute extremes. So this is my max. This is my min. And then these points were stuck in the middle. So I'm going to say absolute max of 364 at 13. Absolute min of negative 648 at x equals negative 9. So the 2 points, the C values didn't matter. I got one of my extremes was at A. The other extreme was at B. So that's the graph kind of looks like this. Yeah. So here were my 2 C values, and they just kind of got stuck in the middle. I will make a note because we talk so much about it. These are your local max. So negative 3 was a local max of 108. And then the 7 was a local min. But the theorem doesn't apply to local extremes. The theorem just tells you will have one maximum absolutely and one minimum absolutely. That's all the theorem guarantees. But, I mean, you still have the ability to figure out the locals. I mean, we already have done it several times. But the theorem doesn't guarantee that that's going to happen. That's the power of a theorem. It's like, it's a guarantee that you're going to get what you're looking for. Which you can probably imagine when we get back to business, which is coming very soon, not in today's lecture, but we're going to get back to business at some point. Maximums and minimums become very important, right? And to be guaranteed that you can find a maximum value or a minimum value, especially when we're talking about money, is important. It's an important thing to be able to predict and to plan around and to focus your attention on those extreme values. I know we don't do problems about weather in this class. That would be more of an environmental science or even just natural science generally. But weather is like that, right? You have the extreme highest temperature of the year, and you've got the extreme lowest temperature of the year. And you can see, I'm not going to do it, but you could probably intuit that calculus can be very useful in making those types of predictions. All right, let's do another one. Shoot, I lost track of where I'm at. Let's see. So we did 2, 3, 4, 5, 6, 7, 8. I hope I'm not off by too much, but I think we're at 8. X to the 4th minus 50x squared plus 11 on the interval -4 to 10. All right. So again, we have A, we have B, and then you use the derivative to find C. So f prime of x, 4x cubed minus 100x. And then you try to find a C value. So you're going to set this equal to 0. Now, normally cubic polynomials are difficult to solve. In some of my previous lectures, I would have to give you a hint in order to be able to solve a cubic. But in this particular one, because there's only 2 terms, I can factor out an x. I can factor out a 4x. And it becomes much easier to solve. So I've got 4x is equal to 0. Now I do have to solve that one, right? I should mention that I've done problems where I just divided by 4 and it didn't give you an additional critical value. But this is not just a 4, this is a 4x. So that you can't just ignore it. That's a critical value. That's your C1, I guess, if we're keeping track. And then we have this one, x squared minus 25 equals 0. So add 25 to both sides. You get x squared equals 25. Then you take the square root. And don't forget that you have 2 possibilities. Plus or minus the square root of 25. So you've got -5 and then you've got +5. So altogether, there are 3 C's. You've got your C1, you got your C2, and you got your C3. And again, you don't really even have to use the letters C. All right, I keep referring it back to the theorem. So if you didn't use the letters C, it's not going to change the results. These are all X's. Everything is an X. Even that's an X, and that's an X, and that's an X. And the only number that's not an X is F, right? F of X is, well, F is the name of the function, and then X produces the Y value. So this is actually the same thing as Y equals, and you know that. But every other value on the board here is an X value. But we use letters like A, B, and C so that we can keep track of who everybody is. All right, so now let's check. Are all of these in the interval? So here's 10. Here's -4. Sorry, you can't see that. There's 10. There's -4. So 0, is that in the interval? Yeah. Check. 0's in the interval, yeah. -5. Not in the interval. Negative 5 is outside the interval. So it's not inside the interval, so I can just ignore it. Yep, that one's gone. And then positive 5, yep. That one's in the interval. So I only have 2 additional critical values. I've got 0 and 5 are in this interval from negative 4 to 10. All right, so let's plug them all in and see who's the max and who's the min. F of negative 4. So I've got negative 4 to the 4th minus 50 times negative 4 squared plus 11. Negative 4 to the 4th is the same as 16 times 16. That's 256. Negative 4 squared is 16. 16 times 50, and that's a negative, so that's negative 800 plus 11. So negative 800 plus 11 plus 256 is negative 533. So far, that's the minimum. But you know, when you first start this, of course it's the minimum, right? Now let's do 0. Oh, that's easy. That's just 11. I don't even have to do any work. 0 to the 4th, that's 0. 0 squared, that's 0. Times 50, that's still 0. And then plus 11. So far, that's the min, that's the max. Let's go to 5. So I got 5 to the 4th minus 50 times 5 squared plus 11. 5 to the 4th is the same as 25 times 25. Just trying to save steps. 5 squared is 25 times 50. So that's negative 1250 plus 11. I got negative 1250 plus 11 plus 625. That is negative 614. Oh, we got a new winner or loser, right? The biggest loser. Negative 614. That's my absolute min so far. So I know this is out of the running. Yeah, somebody's already gotten smaller than that. All right. It's a race to the bottom. Who can be the smallest? All right, now let's go to the race to the top. I'm pretty sure 10's going to win, but let's go ahead and do it. F of 10. Now watch how nice this is. I love 10s. 10 to the 4th, just put 4 zeros. Yeah, 10,000. 10 squared is 100 times 50. 50 times 100 is 5,000. Yeah. I mean, 5 times 100 is 500. So 50 times 100 is 5,000. And then plus 11. I don't really have to do this on the calculator, but I will. 5,000, negative 5,000 plus 11. I don't want to get off by a little bit. See, those funky 9s and 8s. And then plus 1,000. Oh! We even got a bigger loser. Yeah. So this guy's out of the running. Sorry, kid. You thought you were low. You thought you were low, but there's always somebody lower. So that's our absolute min. And this little 11 is actually our absolute max. The graph kind of looks like this. Yeah. Oh, actually, no. Kind of looks like that. No, it doesn't. Look at my math is so wrong. That's 5,000. That's 10,000. I'm so glad I drew the picture. Never trust your calculator. I said I would do it on the calculator because I didn't want to screw it up. I ended up screwing it up. Negative 5,000 plus 11. Rewind. And then plus 10,000. I didn't hit enough zeros. Whew. I'm so glad I drew the picture. Yeah. This graph kind of looks like this. So at negative 4, it was this number. At 0, it was this number. At 5, it was this number. Actually, negative 4 was more like right here. At 5, it was this number. Which, by the way, is now the absolute min, 614. And then absolute max is 5,000. So this is now the absolute min. Sorry, 11. I almost called you the winner for a minute until I checked my math. And the absolute max is, in fact, 5,111. So just in case you looked aside for a minute and didn't catch that, let me write everything out. So we have absolute, or also known as global maximum, is 5,011 at x equals 10. Absolute global minimum is negative 614 at x equals 5. And this rough sketch just was a aid, visual aid. Aid? I think that's how you spell aid. If it's aiding you. All right. Assistant. I like that word better. Visual assistant or a visual aid. All right. How are we doing on time? It's been about an hour. I think we only have one more. I'm going to stop with number 9. And maybe like a couple homework problems that you'll have to go out on a limb to solve, but I think you can handle it. You've seen enough. I don't want to keep you here for much longer, but I do want to make sure I get this one type of function in. This is a exponential function. X to the 8th e to the negative x squared on the interval negative 1 to 4. So we haven't seen any of these in this lecture, and I just want to make sure that I get them in there because we may be using these types of functions for applications. In fact, I think we might have already seen some like this in the law of diminishing returns. But let's talk about closed intervals now and the theorem. So we're going to, at some point, we're going to plug in these numbers. We could do it now or we could do it later. Let's go ahead and take the derivative. And again, I really want to make sure we don't forget some of our basic rules. This is a product rule. Yeah, so sometimes putting a dot here is very helpful. So we have the derivative of x to the 8th. That's 8x to the 7th. Times e to the negative x squared. Plus x to the 8th. Times, let me use parentheses here, the derivative of e to the x squared. Well, e to the negative x squared. So it's e to the negative x squared times the derivative of negative x squared, which is negative 2x. Chain rule. Product rule. All right. We haven't used those at all in this lecture. We've had just easy polynomials. So this is like the worst it could possibly get. And so now we're going to set this thing equal to 0. Let's clean it up a little bit. There's not much we can do with the first one. The second one, this negative and this positive will make negative. That's 2x to the 9th. And then e to the negative x squared. Let's factor out 2x to the 7th, e to the negative x squared. That'll make this a 4 minus x squared. All right, double check that, by the way. 2 times 4 is 8. And then x to the 7th, e to the negative x squared, check. 2 times negative 1 is negative 2. So, I mean, there's an invisible negative 1 right there. So 2 times negative 1 is negative 2. X to the 7th times x squared is x to the 9th. And then e to the negative x squared. All right, we're going to set all three of these to 0. 2x to the 7th equals 0. There's two products here. E to the negative x squared equals 0. And 4 minus x squared equals 0. This is probably the easiest one. Divide by 2. X to the 7th equals 0. So x is equal to 0. Right? I'm not even going to show the step. If x to the 7th power is equal to 0, then the only way that could be 0 would be 0 times 0 times 0 times 0, 7 times equals 0. So that's taking the 7th root of 0, which is not even worth writing down. That's just going to be 0. I've told you this before, and I'll probably say it again. This is never 0. So we can ignore that. E to any power is always a positive number. Even if the power is a negative number, doesn't matter. It's just a very, very small positive number, but it's never equal to 0. So you can ignore that. This one you can actually solve. I'm going to solve it in an unorthodox way. I'm going to add x squared to both sides. So the x squared is on the right, and then I'm going to take the square root. And don't forget the plus or minus. So I'm going to get x equals plus or minus 2. All right, so I got my critical values. These are my C's. I got 0, 2, and negative 2. But look at your interval. Yeah. One of these does not belong. Negative 2. It's not inside. It's not between. That's what it means to be inside. Between these numbers, you're inside the interval. So we only have 2 critical values that we need to check. We need to check 0 and 2. All right, and we need to also check the endpoints. So f of negative 1 is negative 1 to the 8th times e to the negative 1 squared, which is 1 times e to the negative 1, which is 1 over e. That's the exact value. I could put it into a calculator later. And again, be really careful with double negatives. I have seen people get all the way to this step and accidentally make it positive. That's actually 3 negatives, right? It's a negative 1 times another negative 1 times another negative 1. So it's still negative. Let's try 0. 0 to the 8th power times e to the negative 0 squared, which is 0 times e to the 0, which is 0 times 1, which is 0. All right, be very careful. I mean, you do have to verify that it actually equals 0 and not 1. So it's because you're multiplying 0 times 1 that it becomes 0. It's those little things that if you just wipe over it, you might miss it. And by you, I mean me as well. Because I'm a person just like you. You know, I make the same type of mistakes that anybody makes. It's one thing that math does not discriminate is types of mistakes that human beings make. We all make the same mistake. 2 to the 8th. Ouch, that's kind of big. I'll give you a hint. This is the one that I always remember. And this is because I'm looking forward to, I mean, I love teaching math, but I'm also looking forward to my life after math. We call it the aftermath. When I'm 64, I'll be done here. And so that's 2 to the 6th. 2 to the 6th is 64. So 2 to the 7th is 128. So 2 to the 8th is 256. All right. And if you can't keep those big numbers in your head, bust them out on your calculator. I'll probably use this in a minute anyway. I'm trying to hold off as long as I can. And then e to the negative 4, right? Because 2 squared is 4, and then the negative's on the outside. Again, very important. If you type that in your calculator and you put negative 2 squared, it'll tell you positive 4. But it's actually 2 squared, and then it's negative. So that's 256 over E4, or e to the 4th power. All right. And then I have to check this one last. 4. So f of 4 is 4 to the 8th power times e to the negative 4 squared. It's negative 4 squared. That one I would never be able to do that in my mind. I won't live to be that old. So it's going to be 4 to the 8th power, 65,536, e to the negative 16. All right, so how can we tell? I can already tell which one's the min, right? This is a positive number, 1 over e. This is a positive number. This is a positive number. So I already know the min. 0 is the min. All right. Which kind of makes sense because if you think about this function, it's going to go down to the ground, to the x-axis, and hit the x-axis at 0, and that's it. That's the lowest it goes. So it kind of goes like this. And it hits 0 at 0. Yeah. But then it goes up. And the answer is which one of these numbers is the largest? So that's where you're going to need your calculator. So you're going to do E, and then you're going to go 1 over. So I'm doing my approximations. 0.36. You don't need very many decimals. Just a couple decimals will be fine. I don't think that's going to be the winner. All right, let's do e to the 4th. So 4, then e. All right. Then I do 1 over. So there's a 1 over button. And then multiply by 256. That's 4.7 or 4.68. Actually 6.9 if I'm rounding to 2 decimals. Turns out you don't really need more than 1 decimal, but what the heck. And then my last candidate here, 65,536 over E16. Let's see if you're bigger than that. So 16th power E, whew, that's a big number. But then 1 over, that puts it in the bottom, 1 over, and then times 65,536. All right, so this is the winner. There we go. So to summarize this, absolute min of 0 at x equals 0, absolute max of 4.69 at x equals, what was that, 4? No, 2. 4 was what the power came out to be after I plugged it in. All right. So this one was x equals 4. This one was x equals -1. So those ones did not win. Yeah, and then these are the winners. All right, well, that was the theorem on absolute extrema. So do your homework, see if you can get through all 10 of them. I only had time to do 9 examples, but you know, I got to leave something for you to play around with. We've only got one more lesson. We're going to go back to the business math in the next video, but until then, keep working hard, keep your head up, keep your mind focused, do your homework. I'm Dr. Jordan. I'll see you on the internet.